Let's see, today we're going to talk about the comparison tests. There it is, my pen is connected, and let's see, blah blah blah. So we're going to put the comparison test. There's two comparison tests. One is called the direct comparison test, and the other one is called the limit comparison test. The direct comparison test is used in situations like the following. When you want to find out whether this series converges or diverges, you take this sequence that makes up the series, which is 1 divided by n squared plus 2n plus 1, and you compare it with 1 over n squared. And because 1 over n squared is bigger than 1 over n squared plus 2n plus 1, and you let that, we call it Bn, and the sum as n goes from 1 to infinity of 1 over 2 to the n power converges, because it's a p series with p equals to 2. Then the original series, which is the series that goes from 1 to infinity of 1 divided by n squared plus 2n plus 1, converges as well by the comparison test. So when you use the comparison test, you usually are going to compare with a p series or with a geometric series. Let's take a look at another example. Suppose we want to determine whether this series converges or diverges. This time we have 5 divided by 2 plus 3 to the n power, and we want to see if this series converges or diverges. So we start by writing out 5 divided by 2 plus 3 to the n power, and then this is less than 5 over 3 to the n power, and we call this Bn. Since the series corresponding to Bn, that is this 5 times 3 to the n power, it's a convergent geometric series. The series 5 divided by 2 plus 3 to the n power converges again by the comparison test. Now, suppose we have this series, and we want to decide whether it converges or diverges. So we have the sum as n goes from 2 to infinity of the square root of n divided by n minus 1. The series doesn't necessarily have to start at 1. In fact, this series, if doesn't start, is not valid when n equals 1. But still, so we have a n equals to the square root of n divided by n minus 1, and this time this is bigger than the square root of n divided by n, because n has a smaller denominator than this other sequence, which it's n to the 1/2 power divided by n to the 2/2, and this is 1 over n to the 1/2 power, and this is what we call Bn. Now, since the sum as n goes from 1 to infinity of 1 over n to the 1/2 power, it's a p-series that diverges because p is equals to 1/2. Then the series that goes from n equals to 2 to infinity, which is the one that we're going to compare to the original series, diverges as well, because it's nothing more than one less term than the p-series. So sometimes people call this a partial series because it's just part of the p-series, partial p-series. So because this diverges, then the original series diverges because it's bigger than this series. So the series as n goes from 2 to infinity of the square root of n divided by n minus 1 diverges as well by the comparison test. So the comparison test basically just, you have a series and you compare it to a bigger series. If the bigger series converges, then the smaller series converges, and if the smaller series diverges, then the bigger series diverges. And usually the series that you compare it with will be like a p-series or a geometric series. Now sometimes the comparison test doesn't work or is difficult to apply. So for example, in this case, if you have the sum as n goes from 1 to infinity of 1 plus 2 to the n divided by 1 plus 3 to the n, then an, which is 1 plus 2 to the n divided by 1 plus 3 to the n, it's less than 1 plus 2 to the n if we drop the 1 from here, from the denominator, but then after that it will be bigger than 2 to the n divided by 3 to the n, so these are like contradicting statements, so the direct comparison test is not going to work. However, an, which is 1 plus 2 to the n divided by 1 plus 3 to the n, behaves as n approaches infinity as 2 to the n divided by 3 to the n, and we're gonna let this be Bn, and we're gonna use something that is called the limit comparison test. The limit comparison test goes like this: you take the limit as n approaches infinity of an divided by Bn, and if that limit is positive, so in this case it's the limit as n approaches infinity of 1 plus 2 to the n divided by 1 plus 3 to the n, and then times 2 to the n divided by 3 to the n. That's the same as dividing by actually, alright, I'm going to put it over here, 2 to the n divided by 3 to the n, like this, and then I'm going to go ahead and erase it from here. Now, this is just the limit as n approaches infinity of 1 plus 2 to the n divided by 1 plus 3 to the n times 3 to the n divided by 2 to the n. And then this is the limit as n approaches infinity of 1 over 2 to the n power plus 1 divided by 1 over 3 to the n power plus 1. This is basically you divide the numerator divided by 2 to the n and divide the denominator by 1 over 3 to the n power. Anyway, this is equals to 1. This limit is equals to 1. The limit comparison test says that if this guy is positive, then the series, the original series, is going to converge if the corresponding series converges, or is going to diverge if the corresponding series diverges. Which is the corresponding one? The one with Bn. So this series 2 to the n power divided by 3 to the n power is just a geometric series, or a multiple of a geometric series. So this series converges. because the ratio is 2/3. And so therefore the original series converges by the limit comparison test. So the sum as n goes from 1 to infinity, 1 plus 2 to the n divided by 1 plus 3 to the n converges by the limit comparison test. And if I take a look at this other series, sum goes as 1 to infinity of n squared minus 5n divided by n q plus n plus 1. And if you try just the direct comparison test, such as an equals n squared minus 5n divided by n cubed plus n plus 1. And if you drop the n and the 1 in the denominator, you get n squared minus 5n divided by n cubed, and then this is less than, if you drop the 5n, n squared over n cubed, so you get 1 over n, and you can call this bn. So then this would be less than the sum as n goes from 1 to infinity of 1 over n. Because this is a divergent series, it's a harmonic divergent series, it doesn't mean that the smaller series diverges. It only means when you use a comparison, if it's the bigger convergence, the smaller converges. So we cannot use the direct comparison test here either. But an is still going to be n squared minus 5n and divided by n cubed plus n plus 1. And still, as n approaches infinity, we get n squared divided by n cubed, which is 1 over n. And we're still going to call this bn. And if we take the limit as n approaches infinity of an over bn, this is the limit as n approaches infinity of n squared plus minus 5n divided by n cubed plus n plus 1 times n over 1. And this will be the limit as n approaches infinity of n cubed minus 5n squared divided by n cubed plus n plus 1. And the limit is equals to 1, which is positive. So then the limit comparison test says that the original series, so I'm going to go ahead and erase this. And I'm going to say the original series, n going from 1 to infinity, n squared minus 5n divided by n cubed plus n plus 1, and diverges by the limit comparison test because the series corresponding to bn, which is the harmonic series, diverges. So the limit comparison test says that if the series corresponding to bn diverges, then the series corresponding to an diverges as well. Okay, this is the comparison tests. Thank you very much.